Okay, but that's the turbulent plume. So that turbulent plume only started at height after the flow reached a particular strength. What about the laminar plume that started at the nozzle and persisted for some time until the turbulence was triggered? So you can apply a similar dimensional approach to solve this problem, but it's a little more complex because if we have a laminar plume, then we're saying that the viscosity and the diffusivity are important. So again, we have the imposed buoyancy flux at the nozzle, but we've now also got this viscosity and diffusivity. So if you look at the number of parameters there, we have 3 parameters and 2 units, which means we have one non-dimensional number in the problem. And you can pick that as being the Prandtl number. But the problem is now, because we've got these non-dimensional numbers in the system, we actually have to go and solve the equations, or at least look at the equations to determine the form of the radius, the velocity, and the buoyancy. So if you just try and do it dimensionally, you'll see there are multiple ways you could form the units correctly because there are these non-dimensional numbers in the system. So you'd have to look at the equations. I'm not going to do that here, but if you go and look at them, what you'll find is you'll get the radius going like this, which means that the width of the laminar plume increases more slowly than the turbulent plume. And you can see that very clearly in the experiment. The vertical velocity, in fact, doesn't depend on height at all. So vertical velocity is constant in this laminar plume. And then remember, it slows down quite a lot when you reach the turbulent plume. And lastly, the buoyancy reduces, but it doesn't reduce anywhere near as fast as it does for the turbulent plume because it's relying on a diffusive transfer of the ambient into the plume, whereas in the turbulent regime, it's got this turbulent entrainment, which is much more efficient. And so these constants that we've used here, these C1, C2, and C3, they are not universal because they depend on the non-dimensional Prandtl number. But one thing you should note here is that if we form the Rayleigh number, so it's a buoyancy by a length scale cubed divided by the viscosity and the diffusivity, then if you chuck those in, you'll find that you get the Rayleigh number goes like the height to the half. So this means as you move up the plume, your Rayleigh number of this flow is increasing. And as we saw from the example of various plumes, when you move from a small Rayleigh number to a high Rayleigh number, your plume transitions from laminar to turbulent. So what we see in the lab is exactly what we expect. If you let a laminar plume evolve for long enough, it will transition to a turbulent plume.